channel transition, particularly when a channel bed is provided with hump. So as we discussed already in the previous class, if you plot the variation of specific energy with the depth of flow, the flow depth versus specific energy behavior can be depicted as follows. So for a given Q, as y tends to be very small, the specific energy becomes infinity, or this curve joins the specific energy axis on a asymptotic way. And when the y tends to a very large value, the specific energy tends to equal to y. So for a given discharge, let us say I take a specific energy at a particular section as E1. So for this specific energy for a given discharge, there are two possible depths. One depth is the supercritical depth, which I depict here as y1, let us say. Another the subcritical depth, which I depict here as y2. So this zone is subcritical zone and this zone is supercritical zone. Now let us take the channel with a hump situation. So for discussion purpose, we are taking only a rectangular channel. Okay. So let's say this is the channel bottom, and this channel is provided with a hump of height, let's say delta z. Originally the flow is happening with a flow depth, let's say y1 throughout. Okay. So let's say this section is section 1. Now our interest is to study what happens to this flow depth when a hump is introduced on the channel bottom. Okay. So as you see from the specific energy curve, let's say this section 1, and I take another section here, this section 2 over the hump. Now the energy at section 1, specifically section 1, can be written as y1 plus q square by 2g a1 square, or you can write y1 plus q square by for rectangular section. Okay, I am also assuming that we are discussing this flow condition only for subcritical flow. Okay, so now as you see here, when it comes to section 2, the channel bottom is now raised by a depth of delta z. So the specific energy at E2 will reduce by an amount delta z. So if you look at specific energy curve here, and I reduce, let's say, the specific energy by delta z. Okay. So now the new specific energy comes here, which is E2, and the depths corresponding to that is this one for subcritical and the other one for supercritical. So since our interest is subcritical flow, the depth is this one. So the original depth was this, it has dropped to another depth. So the flow is happening through this. Okay, it will experience a drop of depth here. Let's say this is the y2. So there will be a drop of depth. Okay. Now if I increase the delta z further, okay, so I am reducing the specific energy again at section 2. So this specific energy line will move again to the left further, and the depth will fall further. Okay. If I continue like this to an extent where z becomes, let us say, is equal to a maximum z which we can increase, which will correspond to a minimum energy. Okay, at that point the depth here will fall to yc. Okay, now in case I increase the depth further, means the hump height further, more than this delta z maximum, theoretically the flow cannot take place, because energy has already reached the minimum. If I reduce it further, what happens is, because of the hump here, the depth here happens to be or continues to be yc, but for the flow to happen, the upstream condition adjusts itself, and let's say this is the original E1, it goes to the new E1. Let's say E1 dash. Okay, so on this side will be that whatever this, let's say I call it as delta Z1. Okay, that's the height. So corresponding to this, we have to estimate what is the value of, let's say, Y1 dash. So essentially what happens is, when you provide a hump, the flow depth over the hump will drop if it is a subcritical flow. Okay, because specific energy is reduced. Okay, and as you keep increasing the hump height, the specific energy will further reduce, resulting in a lesser flow depth. This will continue till the time the delta Z reaches a maximum value, when there is no further decrease in energy possible. Where is the minimum energy? Okay, if we happen to increase the hump height more than the maximum that is physically possible, the flow depth in the upstream side will adjust itself, and at the section 2 the depth will remain critical depth. Now let's take one small problem. It is from GATE exam 2008. Let's say there is a channel, it has a discharge of, let's say, 16 meter cube per second. The width of the channel is 6 meter, and the depth of flow at section 1 is 1.6 meter. Okay, now what is the specific energy E1 at section 1? This will be 1.6 plus 16 square by 2g, and this one B is 6 square into Y1 is 1.6 square. Okay, so this value will be, I think this comes out to be 1.74 meter. Okay, now the question is, what should be the maximum hump height? What should be the maximum hump height such that there is no change in the upstream depth? Okay, there is no change in the upstream depth. So that means till the time delta Z reaches Z maximum, there will be no change in the upstream depth. So we have to find what is the Z maximum. So this will occur when the second section has a critical depth. Okay, so the energy at section 2 will be E1 minus delta Z. So we are interested to find what is that maximum delta Z, okay, which will result in no changes in the upstream direction, upstream condition. So the delta Z maximum will be equal to E1 minus E2. Now the E2 is the energy at second section, and because when Z is maximum, the condition happens to be critical, we can find the EC value as, for rectangular channel, 1.5 Q square by G to the power 1 by 3. So this value comes out to be, to find out this value, it comes out to be 1.34 meter. So the maximum height to which hump can be raised is 1.74 minus 1.34, that happens to be 0.4 meter. Now let us say we increase the height to delta Z as 0.5 meter, that is more than maximum. So in this case what will happen, as we discussed, originally E1 was the upstream energy. Now let us say we have hump height more than the maximum hump height. So let's say we have delta Z as 0.5 meter. Now if you look at the specific energy curve, originally the E1, it corresponded to a subcritical depth of Y1, which is 1.6 meter. Now, when the hump height is more than what is possible for the minimum energy, the upstream depth will readjust itself in such a way that the flow depth over the hump continues to be YC, whereas the upstream depth changes to a new depth of Y1 dash. So now the task is how to find this Y1 dash. So let's come back to the same concept. So we have specific energy at section 2 as specific energy at section 1 minus delta Z. So now we are interested in the new value. So E1 dash will be E2 plus delta Z, because E2 has a critical condition. So E2 becomes EC plus delta Z, and as for previous calculation, this is 1.34 plus 0.5, so this becomes 1.84 meter. Now the same E1 dash is also equal to Y1 dash plus Q square by 2G B square Y1 dash square. Now this equation, E1 dash is equal to Y1 dash plus Q square by 2G B square Y1 dash square, can be directly solved in your own calculator, or we can also use trial and error approach. So let us go by trial and error approach for the time being. Let's say assume that initially Y1 dash value, I assume the first assumption as 1.7 meter. Why I assumed a depth more than 1.6 meter? Because the specific energy has increased, the corresponding depth in the subcritical flow is more than the previous one. From the curve you can see it is more than the previous one. So I am assuming it as 1.7 meter. So for an assumed value of 1.7 meter, this E1 dash, if we calculate by substituting Y1 dash is equal to 1.7 meter, I find this value to be coming as 1.82 meter. But this is not equal to 1.84 meter as it is desired. So now let us say as second assumption, I am taking 1 point, it's only a marginal difference is there, so I take it as 1.72 meter. So this new E1 dash will become, if I estimate now, this comes to be exactly 1.84 meter. So the new Y1 dash is 1.72 meter. So the upstream depth will increase from 1.6 meter to 1.72 meter. So in summary, if you have a channel, rectangular channel with flat bottom, slope, provided with a hump, as the hump height is increased, the flow depth over the hump will keep dropping for a subcritical flow condition. This phenomenon will continue, this flow depth dropping phenomenon will continue till the time or till the situation is such that the hump height is maximum, under which condition the depth here will be critical. Now if I increase the hump height to be more than, let us say, critical height, then the flow depth continues here to be critical, whereas the upstream depth is found to increase and the flow depth will continue to be critical. So the new flow behavior will become this way. So this depth now becomes, in this problem it is 1.72 meter, which was originally 1.6 meter. If the delta Z is less than delta Z critical, there is no change in the upstream depth, whereas the downstream depth will keep on reducing. That's it.